So this is the question. So suppose you have, okay, this is one of the kind of common scenes in space movies, science fiction movies. You have a spaceship that is trying to run away from a star which suddenly becomes a black hole. And then the black hole starts attracting the spaceship with a very strong force. It has a very strong gravitational force, so it attracts with a very strong gravitational force. So the question is, suppose in our real life, the sun, for some reason, becomes a black hole at an instant. So what would happen to the trajectory of Earth? Don't send your messages yet, I didn't start it. So the possibilities are that since the sun becomes a black hole, it will attract the Earth much stronger. So the Earth will fall into the sun. That is one option. The second option, the Earth just runs away, flies away. And then the third option, nothing will change. It will just follow its trajectory. Well, this number is valid for Turkcell, Avaya, Vodafone, whatever you have. Sorry, the question? No, this is free. Don't worry about that. So A is competing with C. Okay, if you had already sent your answer, just ask your neighbor if they have the same answer or not. Remember that just because many people are voting for A doesn't mean that A is correct. Okay, now the answer is not A. Okay, so what is wrong with A? Yes? So we have this force formula. It is the magnitude of the force is proportional to the Newton's constant times the product of the masses divided by the distance squared. And we had already seen that whether these masses are spheres or points doesn't really make any difference. The only important thing is its mass and the distance of the centers of those spheres. If the sun, when the sun becomes a black hole, its mass is the same, as your friend has pointed out. Its center is at the same position. So neither its mass, neither the mass is here, nor the distance here, nothing changes. So the force that we will feel on Earth will be exactly the same. On the surface of the black hole, of course, the gravitational force will be much stronger than on the surface of the sun because the black hole is a much smaller object. Yes? Well, we know that mass is there and mass is the same. Black holes have a mass. Of course, the formation of black hole is a different story. But we are just assuming, in the question, we are assuming that the sun suddenly becomes a black hole. The sun will never become a black hole. The mass doesn't change. Even if the mass just changes, suppose the black holes usually form in supernova explosions where the mass of some of the mass of the star just blows away. So the mass gets reduced. But in that case, even the Earth will not fly away. It will just be, it will enter a different orbit around the black hole. Well, since the force is the same, it will not fly away. It will just follow its earlier trajectory. The orbit of the Earth will not be affected at all. Now, what does change is, in fact, now when we study the forces here, the force inside and out of the galaxy, now you see the force inside the galaxy just increases linearly with the distance from the center. The force out of the galaxy, it just decreases as 1 over r squared. Well, galaxy is not important here. You are just inside this mass distribution or outside this mass distribution. So if you take the same thing for the sun, if you are at the center of the sun, you will not feel any gravitational attraction. As you go out of the sun, toward the surface of the sun, the gravitational attraction you will feel will increase linearly, and then it will start decreasing as 1 over r squared. Earth is somewhere over here. Now, if the radius of the sun gets smaller, with mass constant, so you will just follow this line. So if the radius is smaller like this, then as you go towards the surface, it will increase much faster. But if the radius is smaller with the same mass, it just means the density is larger. This density over here is larger. But if the density is larger, the slope of this line is much larger. So it increases very fast, linearly, and when you are out of this more compact sun, it starts dropping as 1 over r squared. But this curve is always the 1 over r squared curve, and what happens here doesn't change at all, whether the sun is a very large extended object or a very small compact object with a high density. The force that we feel here only is affected by the total mass of the sun, not by its size. Well, let's do a similar problem. This time the sun doesn't become a black hole, but suddenly it disappears. So the mass goes to 0. by some magic. Again, the question is, what will happen to its trajectory? So since it was in an almost circular orbit, you might say that, okay, it will just spiral away, going further and further away from the sun. Or you can say that it will just go in a straight line away from the sun. Or just like the previous question, nothing will change. It will just keep on going in its orbit. Okay, so this time the majority has the right answer. So it is B. What is wrong with A? Okay, A was the second choice that got the most votes. So what is wrong with A? True. True. The thing is, since sun is not there, there's no force acting on Earth. Since there is no force acting on Earth, it cannot accelerate. It will have zero acceleration. But a spiral means that if it's spiraling, it means that its velocity vector is constantly changing with time. That is, a spiral means it's accelerating, so it cannot accelerate. Yes. The other? Well, we are just ignoring everything else. It's just the sun and, well, I just said that. Well, their effect will be almost negligible anyway. The effect of other planets, the galaxy, it will continue in a straight line to a very good approximation. Now, let's continue with our gravitation. Well, one thing we don't like about this Newton theory of gravitation is that it is what we call the action at a distance. So you have a mass over here, m1. Another mass is over here, m2. And there is nothing to carry the force between m1 and m2. So it's just m2, just like that, feels a force due to this mass m1 from a distance without any contact or anything else that carries the force. Now, you are staying now in this classroom. There's a Japanese student just sleeping on the other end of the world, more or less. It should be midnight there. So he is attracting you. Although there was all this mass in between you, there's all this distance between you, nevertheless, there's an attraction between you and your Japanese colleague. We don't really like that. In physics, we prefer to have things to influence each other only locally. I can just push the desk here. I cannot push that desk over there. I shouldn't be able to push that desk over here. Of course, if you put all the desks in between, if I push this desk, everything in between will carry my force to the other desk, but then there's all these other things carrying the effect from my point to the other point. So here in terms of gravity, at least in Newton theory, there is nothing like that. There is nothing carrying my gravitational effect from this point to the point where your friend is sitting. So we invent something that we call the field. Yes? Well, we still don't know what is the force. That didn't change that much since Newton's time. Well, we of course have the theories. What is force? We have some understanding of force, at least in particle physics. We know what force is. That we will discuss in a few chapters. Ask me again at that time. Now, about the gravitational force in general, we still don't know what it is. We don't even know. There are some new theories which claim that the gravitational force doesn't exist. If you take two electrons, there is no gravity. They claim that there is no gravitational electron between those two electrons. But let's just leave them aside for the time being. Let's stick with Newton theory. there is this one property of Newton's theory of gravitation, this action at a distance which we do not like. At least we can invent something to fix it. And then see if the new theory will tell us something else or not. So that's usually how you proceed. If you have a theory, if there are things that you don't like with that theory, rather than throwing away the theory completely, you first try to fix it. So this hypothesis of the gravitational field is one of the things that we invent to try to fix this, let's say, this feature that we don't like, we would like to avoid, this action at a distance. So what we say is that at each, if I put a mass over here, I have this mass over here. Now this mass, at each point in space, it creates what we call a field, the gravitational field, which we denote by G bar. Now its magnitude is given by this number. Well, the way we define it is that we just put a test mass over here, we calculate the force acting on this test mass divided by the value of this mass and take the limit as this m goes to 0. And this is minus Gn m1 over r squared r hat, minus r hat, yes. Well, this is something we invent. So we say that at each point in space, each mass creates a field at each point in space, so that when I put some mass over here, some second mass over there, this mass m2 doesn't really feel the presence of this m1, but rather it feels the presence of this gravitational field. And the force acting on this mass m2 is nothing but its mass times the field at its position. So we are just looking at it in a different way, rather than saying that, okay, the gravitational force just crosses all this space and acts on this mass. We are just saying that there is a field created by this mass in all over space, and when I put another mass over there, it doesn't really feel this mass, but it feels the gravitational field created by this mass. It is just like I'm imagining that there are all these chairs in between my desk and all that desk, and when I push this desk, that table will feel the push because of all the things in between. And in this case, it is the gravitational field that places all the chairs in between these two desks. Of course, at this level, it just seems it's a mathematical trick and nothing more. So then the next question is, okay, we invented this mathematical object. Is it physical? Does it have its existence independent of the masses? Now it turns out that it does. It is a physical object. It has influences, and you see that in general theory of relativity. This is a fundamental object of general theory of relativity. And what happens is, for example, if I change the position of this mass 1, in Newton theory, if I change the position of this mass 1, we know that this mass 2 would feel it instantaneously. At that instant, the force acting on this mass 2 is just 0. It will just change. But with this field concept, what happens is, as I move this object, if I move this object here, what happens is it changes the gravitational field just at its near vicinity. But a change in the gravitational field at one point changes the gravitational field at its near vicinity also. So as I move this one over here, gravitational field here is modified because the mass has moved. But since the gravitational field here is modified, it modifies the field here, which modifies the field here. So all these changes are propagated to the other mass. And this change moves with the speed of light. It has a finite speed. It's just like if I push my table here, then that table will feel a push, because when I push this thing, first chair is pushed. That is what I am pushing. My table is pushing the first chair, but the second chair is pushed by the first chair. So the second chair moves because the first chair has moved. The third chair moves because the second chair has moved. So just like that. As you move the mass, it pushes this field, But as it pushes the field, it modifies the field in its near vicinity, which then modifies the field it's at a further distance, further, until it reaches my mass 2. Now, this concept of fields will be more important for us at this level in the second term, where we will be dealing with a similar phenomena, the electromagnetic phenomena. It is electromagnetic phenomena and gravitational phenomena at this level, they are quite similar. And there we will have also these fields, electric field, the magnetic field is exactly the same fields. It will be exactly, we will define it exactly in the same manner. And then we will see that what we call light is nothing but electromagnetic field. So it has its own existence. Gravity also, it has its own existence independent of the masses. That is for next semester. Now, up to this point, now the question of mass. It has been especially famous in the last few years because of the Higgs particle. So do we understand mass? We already have seen one definition of mass. When we were discussing Newton's dynamics, we could define a mass relative to a standard mass. And from that, in Newton's dynamics, okay, this is one place where the mass appears. This is the inertia. It is the resistance of an object to an external force. This is what we call the inertial mass. Then we have another mass. If you look at the gravitational field, Gn times the mass of the object divided by r squared in the r hat direction. Well, here we have another mass. Well, if you remember your electrostatic courses in first year, well, this looks exactly like the electric field created by a charge at rest. The only difference is that, okay, we have a different proportionality constant, and instead of the electric charge here, we have the mass here. So in a sense, we call mass in this expression, it is the gravitational charge of an object. So this mass here is the source of the gravitational field. So this is what we call the gravitational mass. But it turns out that these two, observation tells us that this inertial mass and gravitational mass, they are equal. It's called the equivalence principle. We don't know why. Why should the inertial mass, its resistance to motion, would be equal to its capacity to change a gravitational field, a gravitational force? We don't know why. But it is there. And if it is not there, if it doesn't hold, then we should forget the general theory of relativity, which is the only theory we have for relativity at the moment. This is another question that we don't yet understand why. Well, it has nice, well, before skipping, it has nice consequences. Now let's look at this problem of weightlessness. Now we had already discussed you standing in an elevator. This is the elevator. Here you have a scale. You stand on the scale. Or we had discussed the problem of an accelerometer. So we had a mass attached to the end of the string, and this fixed point is accelerating with an acceleration a. I'm sure you have already solved this problem or a similar problem, saying that, okay, if this is the case, if my system is accelerating with an acceleration a in this way, then this will feel a force in this direction given by m times minus a, and then it has the weight with magnitude m times g, and then you can determine this angle. So how many of you didn't solve this problem like this before this year? So did you solve this problem before in high school or similar problems? How many of you put that force over there? M times minus A. None of you? Are you sure you'd never put such a force? Or in circular motion. This is the tension force. This is the mv squared over r. So how many of you did it like this? Come on, your quizzes are not saying that you are, I mean, from your quizzes I can tell you that all of you did it like this, more or less. You just add a force in the opposite direction to your acceleration. In the center of motion, you add a force in the opposite direction that the force actually is. It's just in the outward direction, the centrifugal force, which doesn't exist. Well, this works, and I'm sure you have gotten the right answer by making such calculations. It works because of this equivalence principle, mainly. How does the equivalence principle come here? Well, let's just discuss it. Now, we had this question. We had the mass, and we had the elevator is accelerating in this direction like this. We had said that it has a weight. Magnitude is mass times g in this direction. There is a normal force acting on it in that direction. If this is the z direction, then we know that the normal force acting on it, we can write it as n times z. The weight we can write as minus mg in the z hat direction. This is a question we had already discussed. So the net force acting on it is n plus w, n minus mg times z hat. If it is accelerating with an acceleration a, let's denote the acceleration by a along z hat. Now in this diagram, I am assuming that this small a is negative to show in this diagram. That means that n minus mg z hat is equal to m times a z hat, or the normal force acting by the scale to you is m g plus a. But remember, this mass over here is your gravitational mass, the mass that creates the gravitational force. This is the gravitational mass. This is your inertial mass. This is from the Newton's second law. Now, this normal force is the weight measured by your scale. So the equality of this gravitational mass, the inertial mass, allows me to just take these two terms into a common m parentheses. So this is nothing but m times, let's say, g prime. Since the inertial mass and the gravitational mass, they are equal, an elevator with an acceleration is the same thing as a stationary elevator with zero acceleration, but put it in a larger gravitational field. They are the same thing. Here we have g and the acceleration. If I just substitute g with g prime and set a equal to 0, I just get this result. Mathematically, they are the same thing. An accelerating reference frame and the reference frame which is in a gravitational field, they are exactly the same. So if you think yourself, if you put yourself into this mass, and if the car is accelerating in this direction, you can just say that, okay, I'm feeling gravity in the opposite direction, plus there's a gravity in the downward direction. So there are two gravitational forces acting on me. So this string will just point in the direction of the resultant gravitational force. That is what we are actually doing here by putting this force over here. Or in terms of your reference frame here. At this point, since your since you are accelerating in this direction, you can just say that you are feeling a gravitational attraction in this direction, sorry. No, okay, since you are accelerating here, you can say that you are feeling a gravitational attraction in the other direction. So that is why you feel your weight. You will measure a weight here. And since in that reference frame you are at rest, which is a non-inertial reference frame, in that non-inertial reference frame you are at rest, you are saying that there is a gravitational attraction in this direction, there is your tension force acting on you in this direction, so these should cancel each other because in that reference frame you are at rest. So the reason why this works is the equivalence principle. Before you ask, you are not allowed to do this non-inertial reference frame in the exam or in your homeworks. So just so I'm telling you so that you know that what you are actually doing is not wrong. I wouldn't like to say that it is correct. It is not wrong, but it works because of this principle. This equivalence principle makes it work. So when you go to a non-inertial accelerating frame, it is just the same thing as a frame at rest, that is an inertial reference frame in the presence of a gravitational attraction. By the way, this also tells you that now we are closed in this room, we are feeling of a downward force, so we believe that Earth is still lying outside, but there is no way that we can be sure that the Earth is outside. It might happen that some strange force had just destroyed Earth or teleported Earth to some other corner of the universe, and now we are accelerating in that direction. That is another possibility. And there is no way we can distinguish the two. There should be no way that we can distinguish the two. This is what this equivalence principle tells us. Well, that principle also tells us that if that is correct, light should bend in the presence of a gravitational force. It looks quite innocent that, okay, we have this equivalence principle, the gravitational mass and the inertial mass are equal, so what? But starting from that, we could say that an accelerating reference frame and the reference frame in a gravitational field, they are the same. If they are the same, then light should bend in a gravitational field. Well, how can we say that? Let's look at this elevator problem. We have a torch here, which we shine some light to the other corner. The light would just go straight if the elevator is not accelerating. But if the elevator has an acceleration in this direction, and let's just assume that initially it's at rest, it has 0 speed, or we are in an inertial reference frame which moves with the same speed as the elevator initially. So there is a beam that shines. Okay, this is the opposite corner. So initially it was at rest. So what we will see is that the light will go and hit this point. But during that time, the elevator, since the elevator is accelerating, it has moved to such a point. It's no longer here, it has moved a bit. But that means if I just draw this displaced, or if I just look at it, I'm the man inside the elevator. So there was this light beam which started here. It was aimed at this point, but since the elevator has moved, the light beam will hit some point over here. Instead of hitting at a distance from the floor at such a distance, it hits from such a distance. So the light beam observed by the man taking the elevator has just bended. But this equivalence principle also tells us that for this man inside the elevator, whether the elevator is accelerating or the elevator is put in a gravitational field shouldn't make any difference. That is our equivalence principle. So he would conclude that he is not really accelerating, but there is some gravitational field acting on him, and the light ray just bends in that gravitational field. So we can just conclude from this equivalence principle that the light ray should bend. Now, because otherwise, if he feels a gravitational field and the light ray doesn't bend, then he could say that, okay, the equivalence principle, if the equivalence principle doesn't hold, then if these two were different, the accelerating reference frame and the gravitational, a reference frame in a gravitational field, if the light ray goes straight, he would say, okay, I'm in a gravitational field, light doesn't bend. If it bends, then he would say, okay, I'm in an accelerating reference frame. So he could distinguish the two if the light didn't bend. But the equivalence principle tells us that you cannot distinguish these two cases. That an accelerating reference frame and the gravitating reference frame are identical. The measurements you make in both of them should be identical. That is the equivalence principle. So our time for today is up. Any questions before you go? Yes, there is one question. Of this one? Well, in fact, because the light bends, we can say that it has an effective mass. Kind of an effective mass. It's massless, as far as we know. But you can assign an effective mass to light has energy. So you can assign an effective mass to light. And that is why you can say that the light in the presence of a gravitational field should bend. Any other questions?